Hey, welcome to Physics 114 Lab. This week we'll be doing radioactivity. We do this lab not necessarily because you'll cover it in as a topic in lecture, but because many of you will be aspiring to take the MCAT, and the MCAT will have questions regarding some of these topics of radioactivity. So specifically what we're going to look at today are differences between alpha, beta, and gamma radiation. In particular, what materials and what thicknesses would it take to stop that radiation to some degree. And then also we're going to look at the half-life, okay? And we'll look at a particular material there and determine what its half-life is. So just a real quick recap. When we talk about nuclear radiation, what radiation means is to radiate out from something. So we're going to start with the nucleus of an atom, and something is going to come out of that particular nucleus because it is unstable. Either it's typically because the ratio of protons to neutrons and the forces that interact between those are the balance is not where it would like to be, so the energy is not its lowest state, so it's going to give off something. And that could be in the form of alpha, beta, or gamma. Alpha is actually a helium-4 nucleus, which means it's 2 protons and 2 neutrons together without any electrons. Beta is an electron. There's also beta plus and beta minus because there is an anti-particle to the electron that's called a positron, but we'll just stick to discussing the beta negative decay at the moment. And finally, the other one we're going to discuss is gamma radiation, which is electromagnetic radiation in the form of a gamma ray. So gamma ray is of the highest frequency as far as classifying electromagnetic radiation. Therefore, its energy is going to be the highest. There are other types to consider. There's also neutron emission, neutron radiation. We're not going to look at that here today, but we'll kind of discuss a few things as we move along. So the idea is that we're going to start out by seeing just how much natural radiation we have. We're going to get a background count using what's known as a Geiger-Müller counter. So we'll use that device to get a set of data. And then we're going to place various different sources. We have an alpha, beta, and a gamma source, and we're going to place those sources underneath, and we're going to try different absorbers. And basically what we're going to do is determine how thick of a particular piece of material would it take to stop half of the radioactive particles that are being emitted from radioactive nuclei. Then finally, after we do the alpha, beta, and gamma, we're going to move over to doing the half-life, and we'll look at a particular piece of material over here. It's cesium that will decay to barium, and we're going to take a look at what comes off of the barium, and we're going to look at the half-life specifically of barium-137, and then we'll compare that to the known value. So coming over to the computer, I have already set up some of the initial things here within Capstone. I've gone ahead and attached the Geiger tube and done some preliminary work. But looking at the exercises, there are a couple other things we need to do. We need to set the sample rate interval. So recall that we can't predict when one particular nuclei that's radioactive is going to decay. But we can look at the average number of decays over a period of time. So what we're going to do is set up the counter here. I'm going to change this to a 30-second interval. So this means it's going to take data it's going to count for 30 seconds and then give us that count number as one data point. And then it will repeat that for as long as we'd like. And so what we're going to do is change the stop condition here to time-based. And I'm going to change that time to 151. So that's 151 seconds. The reason we had that 1 second in there is because after all those other intervals, if we didn't, then it would stop and not give us the last interval, so we'd be wasting 29 seconds of time there, or 30 seconds of data. So in this case, we're just going to waste 1 second, but get the data points that we'd like ahead of time. You'll also notice that I've turned on the statistical averaging, or the statistical totals here at the bottom, so it'll give us min, max, mean, and standard deviation. All we're really concerned with is the mean value. All right, so I'm going to go ahead and prepare the Geiger tube. So typically, this tube, we will remove this cap off and just leave it off for the duration of the experiment. You will hear it beep, and of course that's every time it counts radioactive decay. This cannot delineate between alpha, beta, and gamma. It simply tells us that something decayed, and it counts that. Okay, so it also cannot tell us the energy. So all it's going to tell us is not how energetic it is. So we can't determine which type of particle, but we're going to know because we have known samples here. But we will be able to count the number of decays that happen. All right, so initially we need to get a background count. We need to see how much radiation do we have just here in the room. So I'm going to hit record. And now we wait. So every 30 seconds, it's going to record a value. Looks like we've finished this particular one, so we're going to move on to the next one, and let's first start with alpha, and we're going to use polonium-210. So polonium-210 is an alpha emitter, and recall, I'm going to set down here as close as I can. I'm going to lower this down. I would like to be within 2 centimeters because it does not take very much to stop an alpha particle. Okay, so I'm going to come here and go ahead and start to record the data. Okay, it will not take much to stop an alpha particle. Usually a couple of centimeters of air, your skin, things along those nature. It's because you have 4 nuclear particles that are bound together there as a helium-4 nucleus, right? So it is, relatively speaking, for a radioactive particle, it is highly charged because there are 2 protons there. It's also relatively massive. So it will not penetrate very deep into material before it's going to pick up electrons and lose the kinetic energy. It also has, does not leave the nucleus with a lot of kinetic energy, and so it does not take much to stop it. So it will not penetrate very deeply, okay? But when we're looking at things later, we're going to look at beta and gamma. The beta is an electron. The electron is going to be relatively large charge, but it is very little mass, and it leaves the nucleus with a high kinetic energy. It will penetrate much deeper than alpha. However, it's going to be, it will stop relatively quickly just because it is a charged particle there. And so when we go to gamma, gamma is different because it is electromagnetic radiation in terms of energy. It is highly energetic and with no charge. So therefore, it will penetrate deeply into material. That's what makes gamma rays particularly dangerous in a biological sense. Okay, our 2.5 up for that. The next thing they'd like us to do is take a piece of paper and we're going to place it between. And immediately you can hear that it's much quieter. And I'll begin to take that data. Okay, so we finished the data. I'm going to remove the alpha. And as you see, the paper was enough to block most of that. Next, I'm going to replace that with a beta source. Okay, so our beta source here is strontium 90. And I'm going to do something, and you can hear that's a relatively active source. So half-life on this is 28.6 years, so nearly 30-year half-life. These were brand new in 2002. So the amount of material that was there, we have not gone through one half-life yet. And so therefore, the amount of material that was here, there's still most of that material is still, that's there originally is still radioactive. So it'll be quite some time before this settles down. Now keep in mind, just because you hear a lot of activity does not necessarily mean that it is more energetic than anything. In this case, it is more energetic than the alpha. But we're going to be using polyethylene absorbers, okay? So there are 4 thicknesses of absorbers. So we need to take data without an absorber, and then we're going to take data with the 4 thicknesses that we have here, okay? But we do not want to change the distance of this counter from here once I've set it up. So I'm going to place the thickest absorber here first, even though I'm not going to start with that data. Okay, and that is the thickest that I will have. And at this point, I'm going to go ahead and start the data recording. And also, I'm going to name this simply beta when there's nothing there. But for the next ones, I'm going to use the moniker for poly 1, 2, 3, and 4. So poly 1 will be my thinnest. Poly 4 will be the thickest. I've recorded those already by using a caliper. When we get to the gamma, we're not going to use the polyethylene, we're going to use lead. And for those, I'll use lead 1, 2, 3, and 4, of course, and I've also recorded this already. Okay, so we're finished with the data for that. I'm going to go ahead and insert the first absorber. Start recording. Okay, poly 1 is finished. I'm going to go to the second one. Second absorber and start our data. Okay, so let's go to the third absorber for beta. All right, so next we go to the absorber, polyethylene. Okay, now that our beta decay data, you're going to take each of these thicknesses here. They will be plotted on the x-axis, and remember that the initial one, we had nothing there, but so you'll have 4 data points for that. They ask you to plot the natural log of V naught over V versus chi. So what they mean by that is you're taking equation 12.4, and they've just rewritten that so that you have the minus K, you have K times chi, the absorption constant K, and chi is the thickness. All right, so, and then on the other side of the equation, of course, you have a natural log because you've had to get rid of the exponential. So V naught would be your initial value. So you'll take the value that we had for beta without an absorber there. That value will be the same each time for each of the 4 points. You will simply take that and divide by V, and V would be the count you're getting with the absorber. Take the natural log of that ratio, and that will be your Y coordinate. Then your X coordinate for that plot will be the thickness for that particular V value that you got, okay? So a little different than what you're used to doing, but once you've done that, you should be able to find a linear line. And with that linear line, you can get the slope. And the slope, again, will be the absorption constant K. Because if you think of Y equals mx plus b, with b being 0 in this case, then on the x-axis is the thickness chi. On the y-axis is the natural log of v naught over v. And so then your slope has to be k. All right, once you've done that, in order to figure out how much you would have, how much thickness of this polyethylene it would take to stop half of, in other words, what thickness would it take of this to stop half of the radioactive particles you had here? Now, it's not specific for this particular one, just simply for beta particles that are being emitted from strontium-90. And to figure out what thickness of polyethylene it would take for those beta particles, then you would take that same equation, and there's going to be some point where chi would be would give you 1/2 of your initial count. Okay, so your initial count is V naught. So if you plug that into the equation as well, you'll end up with the natural log of 2 on the for the numerator divided by your absorption constant K. So the half value thickness for this particular material is what you would find by taking natural log of 2 divided by the slope of that line, which would your absorption constant K, okay? All right, so we're going to repeat that exact same process at the end of the data for the gamma source. So let's go ahead and get started on that. The gamma source is cobalt-60, and these were purchased recently here with a, so they should be relatively active, or still a fair bit of radioactive material here, purchased them less than a year ago, and they have a half-life of a little over 5 years, about 5¼ years. So they should be. I'm going to go ahead and place this down here. I'm also going to take my thickest absorber. Okay, so I know that that is going to be close as I can. So let's do it with nothing first. Okay, let's go to our first thickness. Okay, next our second lead absorber. Okay, our third absorber. And the final absorber. Okay, so that completes our section with the absorbers. So for gamma, you'll go do the same thing. Take the, do the same plot with the natural log of E naught over V on the Y, the thickness of the lead on the x-axis, and find your absorption constant K, and then go ahead and calculate what the half-value thickness would be. Okay, once we're done with that, we can now move on to our final step. Okay, for the last part, we're going to be looking at the half-life of material. In this particular case, we have cesium. Now, typically what we would like to do is at least get a few half-lives on a decay curve so that we could be able to calculate some of the constants there in the exponential to get a more accurate value. But cesium has a half-life of 30 years. So we would like you to graduate at some point, so therefore we're not going to look at the cesium. However, inside this material here, inside this container, is material that the cesium is bonded to. Cesium-137 will decay to barium-137. Okay? It will do that all of the time, and typically, actually, barium-137 is stable, so barium normally would not decay. But we're going to look at, talk briefly about this. So cesium, when it decays, it's going to do that through a beta minus. In other words, it's going to eject an electron. And when that electron is ejected, I'm going to round these figures, it's about 5% of the time, it's going to leave the nucleus with about 1.2 what we call MeV, so it'd be mega electron volts. It's the amount of energy it takes to move an electron through 1 volt potential difference. Say from the positive to the negative side, if you're going to think about that. But it's the amount of energy it takes to move that one electron through 1 volt of potential difference. So we're looking at about 1.2 million electron volts, so 1.2 MeV for short. So about 5% of the time, this electron leaves with about 1.2 MeV worth of energy. Okay? When the other 95% of the time, it's going to leave only with about 0.6 MeV. Okay, so it's the same basic electron that leaves, it's just it leaves with a lot more kinetic energy, almost twice as much kinetic energy in 5% of the time. So what about the other 95%? You're still going to be left with barium-137 as the nucleus that remains. However, that barium-137 nucleus, 95% of the time in this decay, is going to have more energy than it would otherwise. So what the barium will then do is give off some of that energy to get down to its lowest energy state, just like the other 5% barium-137 would be. So that barium-137 that has a little bit too much energy, even though barium-137 would typically be stable, it's got a little more energy, so they call this a metastable state. So when you see barium-137m, that's what it's referring to. So a barium-137m nucleus is radioactive, and it's going to decay through a gamma decay. So I mentioned earlier about material inside here. This has a substrate that the cesium bonds to strongly. The barium does not. We're going to use a slightly acidic salt solution called an eluting solution. We're going to run through that and squeeze about 2 or 3 drops out of the bottom of this into a little disc. And so that will only be barium contained in there. The only radioactive materials there should be barium-137 metastable. And we're simply going to put that underneath and begin to look at the number of decays that we have over time, and we will plot that, and so we're going to see an exponential decay. Okay, so we need to make a couple of changes to the software first, so let's go to that. They ask us to create a new page, and we're going to do a graph. And of course, we're going to have Geiger counts on this page. You'll see some of the data left over from last time that won't mean anything to us here. And of course, time is on this axis here. Now, what I'd like to do is change my recording conditions, and also I want to change the rate. So they've asked us to do this at 15-second intervals. And they would like to do about 48 15-second intervals. So that will be 721 seconds. Well, 720 seconds, we're going to add the 1 to make sure we get that last 48th interval in there so we don't waste that. So our stop condition then will be 721. Hit OK. All right, so now we're ready to take data here. The only other thing I need to do is I've got to go ahead and prepare my sample. So I'm going to use this beaker to pour just a little bit of the little eluting solution in there so I can get some inside the syringe. Okay. Can remove the caps from the device. Insert the syringe into the top, and then I'm going to slowly press the fluid through. Okay. Going to remove this cap. Put that cap back on. All right, so because this is a fast decay, I'm going to go ahead and get this started. And now our job is to simply wait. So while that's happening, I'll go ahead and clean up the rest of my materials. And I'll see you when the time is up.
Not unattractive, turn me on tonight, 'cause I'm radioactive, radioactive. It's not a fight, and I'm not your captive, turn me loose tonight, 'cause I'm radioactive, radioactive. Don't be distractive, turn me on tonight, 'cause I'm radioactive, radioactive. Don't be distracted, turn me loose tonight. Yeah, 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 yeah. Oh, yeah, Don't just stare.
Okay, our data is complete. Place that in there to finish decaying. And let's go over here and take a look at the software and see what we can get out of the analysis section. Okay, looking at our data, there are a couple of ways we can analyze this. What we would like to determine is the half-life. Half-life is determined from our initial number of counts, and it's simply how long does it take to get to half that value. So one way is to try to measure it directly off the graph, which this is not always the best method. And so if I start here, I see I have 246 counts, okay? So if I look for half of that, that would be 123. So if I go down and try to find where I have 123, at this point you can see I've dropped below, then I'm above, and then below again. It's really difficult to find the actual value here. So I'm just going to pick this one, and I see that's 124 counts, which is very close to what I had. That'll get us in the ballpark, but then we have to look at the time. That's 195 seconds. Now notice before we had 15 seconds, okay? So 195 minus 15 gives us 180, and so I'm going to go over here to this top page, and I'm going to type in our direct as 180 seconds, all right? So 180 seconds is 3 minutes. That's pretty close, not too bad. It's a little long. Our accepted value is going to be 2.55 minutes. And 2.55 minutes is 153 seconds. So we're in the right realm, but we're definitely not quite as close as we'd like to be. So let's go back to the graph, get rid of this tool, and next we're going to go try to do a curve fit. So when we take a look at the options of different fits we could have, the one that comes the closest here appears to be this guy, the natural exponential. So when I select that, and as long as this is indented, I'll see that I get a relatively good curve fit here. And so at this point, we need to look at the values. So A is 242. That would be our initial starting point. That would have been how many counts we had to start. It would have been like our n naught value that we see in the first equation in the text. Okay, so, and then T obviously is the time. B is what we're interested in. B is going to be the lambda value. Okay, so we see that lambda here is 0.00497. And looking at the lab manual, you'll notice equation 12.2 tells us how to calculate the half-life. So what you would do is solving the first equation, letting n be n naught over 2. In other words, half of our original starting value. If you work through that equation, you would find you would have the natural log of 2 over lambda. So the natural log of 2 is 0.69315. And if I divide that by my 0.00497 value here, I get 139.5. Go ahead and round that up to 140. And recall that 153 was our accepted value, so maybe I'll go ahead and put that here. It's 153 seconds for the accepted value. So you can go ahead and calculate the percent deviations from this. I've done all the hard work for you. Okay, so that wraps up this lab. That will wrap up the course as well. So doing it remotely has definitely been different, but I don't think you'll mind too much that you didn't have to sit and wait for all the data taking there. So hopefully I can speed that up a little bit there in editing, make that not quite so boring to sit through. But hope you learned a little bit about the relative strengths of alpha, beta, and gamma particles, as well as have a much better feel and grasp of half-life and how we find half-life and what it means. Okay? So again, ask your TAs if you have any major questions, and thanks again and good luck.